Hello everyone, welcome to the mind map series, and in this mind map we are going to discuss the chapter of electromagnetic induction. And actually there is another one which is combined with this, which is the result of this one. We'll talk about it, that is alternating current. But first let's talk about electromagnetic induction. I'll just give you a brief idea about what it is. uh, in the last mind map, I think we had discussed that due to a current carrying wire, it was discovered that the magnetic compass could deflect, and we knew that due to this current carrying wire, the magnetic field is getting generated. Now, based on this experiment, several scientists were doing some experiments regarding the interaction of electric field and magnetic field, or electricity and magnetic field. So one of them scientist was Faraday, and he was doing this experiment in which there was this loop, maybe multiple loops, and it was hollow, and this was connected to itself. No extra battery was there, and he was taking a magnet, and he was trying to study the effect of this one. So he had several ideas, but they were not working out, due to which he was getting frustrated, and out of frustration he actually mistakenly threw this magnet out anywhere, and it happened that it passed through the coil. It was just a coil, not connected to any other this thing, any other battery. And there was this little bulb as an indicator over here, and as the magnet passed through this coil, this bulb lit up in absence of any external battery. There was no battery in the system. Even in that case, the bulb lit up. So he thought that this is a great observation, and he did several experiments based on this, after which he gave this law that that is known as Faraday's law of electromagnetic induction. Induction, what is this induction? Induction is basically magnetic field. The magnet is representing magnetic field, right? So magnetic field is giving rise to electricity, or electromotive force, or potential, EMF, electromotive force. This is induction, right? Because there is how is it that one could imagine that magnetic field could generate electricity? But it happened, and this is called induction. Induction. Let me just yeah, I think we'll need slightly thinner one. Yeah. So electromagnetic induction, this is what electromagnetic induction is all about. So based on this experiment and several experiments that followed this one, he devised this law. First of all, we'll talk about something called magnetic flux. Only then we will be able to understand the Faraday's law of electromagnetic induction. So what is this magnetic flux? Let's say magnetic field is in this direction, and there is a loop which is like this, which is perpendicular. For example, uh, this is a circle of a radius r, and electric or magnetic field is going inside the plane. Of course, I did tell you in the last class that this cross represents magnetic field, or any field going inside the plane, and this one coming outside of the plane, coming outside of plane. So basically magnetic field is going inside, and it is crossing, while going inside it is crossing this much amount of area, right? This much amount of area. So the magnetic flux in this case, represented by the symbol phi, magnetic flux is equal to um, the total magnetic field which is passing through it, a constant magnetic field, B, into the area itself. pi r square. This is going to be the magnetic field. But let us say this magnetic field is not constant. It is variable. In one portion it is having a different value, in some portion it is having a different value. Let's say in this portion it is having a b1, in this portion it is having b2, and things like that. In that case, what you will do is find the magnetic flux in this portion and add up with this portion magnetic flux, and in that way, if you have a variable magnetic field, then the magnetic flux would be added one after the other, even if it is changing with area or changing with distance. What you will do is phi is equal to b dA, right? This is the magnetic flux. Magnetic flux हम ऐसे ऐड करते हैं, मतलब simply this is integration. Integration is simply nothing but addition itself, right? Addition of small elements over some distance or some area. तो ये हो गया magnetic flux. Let's say this was perpendicular, right? Because the area, this plane is perpendicular to the direction of the magnetic field. So all of the magnetic field lines will pass through it. Let's say we have another case in which it looks like this, and the area, it is a circle actually, but it is lying somewhat in the z axis. It means it is lying in this direction, and this is x axis and this is y axis. If the magnetic field is now coming in this direction, let's yes, let's take this area, and the magnetic field is going in this direction, and some of the portion is already lying in this direction. For example, this is the area. I'm representing this as a vector. This is the area, and some component is in the direction of the magnetic field and some component is in the perpendicular of the magnetic field. This is the area. This is, let's say, theta, direction of magnetic field B, and then if the direction of magnetic field is this one, then the area which is perpendicular to the magnetic field, only then that will be included in the magnetic flux. Because if you have certain, let's say, a sheet in this direction and the magnetic field is in this direction, then no flux is getting added up, right? Because no magnetic field is crossing the area, it is simply passing through it. That will not be added up. Let's say if this is the case, then I have this area, I'll take a section of this area, component of this area in this direction, and the component which I have taken here, that will actually be perpendicular to the magnetic field. So what you'll do is basically b dA cos theta, integral of this one, okay? Because component of this area in this direction is going to be cos theta, the angle between them is theta. So that was magnetic flux. I hope that was clear. Now if we are clear about the magnetic flux, we will give something called Faraday's law, or I think I should give it here itself. Faraday's law says that the rate of change of magnetic field the rate of change of magnetic flux, it means only when the flux is changing, the magnetic flux is changing, only in that case EMF is getting generated. It means अभी अगर ये फर्स्ट एक्सपेरिमेंट में मैग्नेट मूव नहीं करते रहता तो मैग्नेटिक फ्लक्स कांस्टेंट रहता, जो भी पास हो रहा है इस सोलेनॉइड के थ्रू और इस कॉइल के थ्रू. बट क्योंकि मैग्नेटिक फील्ड चेंज हो रहा है तो मैग्नेटिक फ्लक्स भी चेंज हो रहा है, और मैग्नेटिक फ्लक्स चेंज करने की वजह से ईएमएफ जनरेट होगा. Not just the presence of EMF, magnetic flux is necessary. The magnetic flux should also change with time. So the EMF getting generated is actually equal to minus d phi over dt. Ignore the minus for now, I'll explain it later. So this is the formula for EMF getting generated, rate of change of flux, nothing else. Now अभी हम देखते हैं कि ये माइनस क्या रिप्रेजेंट करता है. देयर इज अनदर लॉ कॉल्ड लेंज लॉ. it says that whatever EMF is getting generated will oppose the source और अपोज द कॉज. इट मीन्स अगर मैग्नेटिक फ्लक्स, अगर ये मैग्नेट इधर जा रहा है तो फ्लक्स जो इसके थ्रू पास हो रहा है कॉइल के थ्रू वो इंक्रीज होगा, बिकॉज द मोर इट इज क्लोजर टू द कॉइल द मोर नंबर ऑफ मैग्नेटिक फील्ड्स विल पास थ्रू द सोलेनॉइड. सो फ्लक्स वहां पर इंक्रीज हो रहा है. तो दिस लॉ बेसिकली टेल्स यू दैट अगर फ्लक्स इंक्रीज हो रहा है और उसके वजह से ईएमएफ जो जनरेट होगा, तो वो जो ईएमएफ जनरेट होगा वो एक्चुअली ट्राई करेगा to balanced out or to stop the increase of flux. Basically Lenz law says कि जो सिस्टम है उसको एज इट इज रहना पसंद है. सिस्टम है उसको एज इट इज रहना पसंद है, मतलब कि जो फ्लक्स पास हो रहा है उसको उतना ही रहना पसंद है. अगर मैं उसको बढ़ा दूं तो ये कॉइल जो जनरेट करेगा इलेक्ट्रिसिटी, दैट विल जनरेट अनदर मैग्नेटिक फील्ड ऑफ कोर्स, बिकॉज दिस इज अ सॉलिनॉइड. अगर इससे मैं करंट पास कराऊं, ईएमएफ विल जनरेट करंट, राइट. अगर इससे मैं करंट पास कराऊं तो ऑफ कोर्स इट इसमें मैग्नेटिक फ्लक्स सॉरी मैग्नेटिक फील्ड क्रिएट होगा. अभी अगर मैं फील्ड्स इधर बढ़ा रहा हूं या मैग्नेटिक फ्लक्स इसमें इंक्रीज कर रहा हूं, तो ये जो एक्सटर्नल जो इसकी वजह से ईएमएफ जो जनरेट होगा उसकी वजह से एक और जो मैग्नेटिक फील्ड क्रिएट होगा, दैट विल ट्राई टू अपोज द इंक्रीज ऑफ फ्लक्स थ्रू इट. उसको जितना फ्लक्स था इनिशियली उतना ही रहना पसंद है. So basically Lenz law tells you that the resultant EMF tries to eliminate or try to oppose the cause. Cause is basically changing magnetic flux. अगर मैग्नेटिक फ्लक्स डिक्रीज हो रहा है, लेट्स से अगर मैग्नेटिक फ्लक्स इस कॉइल से डिक्रीज हो रहा है विद टाइम, वो भी ईएमएफ जनरेट करेगा. बट वो मैग्नेटिक फ्लक्स वो जो डिक्रीज हो रहा है उसकी वजह से जो ईएमएफ जनरेट होगा वो ऐसा जनरेट होगा कि एक्सटर्नल जो मैग्नेटिक फील्ड जनरेट हो रहा है ड्यू टू दिस करंट विल हेल्प दिस फ्लक्स. ताकि वो कम हो रहा है तो उसको और थोड़ा सा हेल्प करो ताकि वो सेम रहे. ये बेसिकली होता है. So this is the Lenz law. For example, I will use an example here. Let's say this is a coil, and इसके थ्रू अगर मैग्नेटिक फ्लक्स पास हो रहा है और वो बढ़ रहा है विद टाइम, तो इसमें एक ईएमएफ जनरेट होगा. बट इलेक्ट्रिसिटी का क्या डायरेक्शन होगा वो हम कैसे डिसाइड करेंगे? या तो ये होगा या तो ये होगा. बट वो हम कैसे डिसाइड करेंगे? या तो इट इज गोइंग टू बी दिस और दिस, राइट. सो द वे वी विल डिसाइड दैट इज बेसिकली हम देखेंगे कि यहाँ पर मैग्नेटिक फ्लक्स इंक्रीज हो रहा है, राइट. तो ये जो कॉइल है, कॉइल की वजह से जो मैग्नेटिक फ्लक्स और मैग्नेटिक फील्ड जनरेट होगा वो ऑपोजिट डायरेक्शन में क्रिएट होना चाहिए ताकि वो अपोज कर सके इंक्रीजिंग मैग्नेटिक फ्लक्स को ड्यू टू द एक्सटर्नल फोर्स. सो व्हाट इज द direction of current such that the field is coming in the left direction? We can apply this thing, right, like this thumb rule. So basically if the current is flowing in this direction, then the field will be in this direction, right. So the current will actually be flowing in this direction when you are increasing external flux in this one. This is one application of Lenz law to decide in which direction the EMF or the current is going to be induced. So this was Faraday's law. Faraday's law. I think we have discussed this one. Flux this and yes, EMF is produced in the loop. No problem. Is there a Lenz law as well here? Yes, Lenz law. The direction of induced current is such that it opposes the change that it has induced. जो भी चेंज हो रहा है मैग्नेटिक फ्लक्स में उसको अपोज करेगा. अगर वो इंक्रीज हो रहा है मैग्नेटिक फ्लक्स एक्सटर्नल सोर्स की वजह से, तो जो करंट प्रोड्यूस होगा वो इट विल ट्राई टू जनरेट एन इलेक्ट्रिक मैग्नेटिक फील्ड विच विल अपोज द इंक्रीजिंग फ्लक्स. अगर वो डिक्रीज हो रहा है मैग्नेटिक फ्लक्स, तो वो एक्सटर्नल जो इंड्यूस्ड ईएमएफ होगा दैट विल क्रिएट मैग्नेटिक फील्ड इन सच अ डायरेक्शन दैट इट विल हेल्प टू increase the flux so that the decreasing flux remains the same. So this is this one. And yes, induced current basically, अगर एक लूप है अगर एक लूप है the wire has no resistance, only this has resistance, then अभी इसमें ईएमएफ जो जनरेट होगा वो तो पास होगा ना कर ये रेजिस्टेंस से. अभी ये इंडक्टर है तो ऐसा थोड़ा है नहीं कि इसमें रेजिस्टेंस नहीं हो सकता है. इवन दिस वायर कैन हैव रेजिस्टेंस इन नॉन आइडियल केसेस. देन let's use this symbol to represent the whole resistance of the circuit, this R. then EMF जो generate होगा वो R resistance ही तो face करेगा. So current I will be simply this I generated by R. So basically 1 by R minus, sorry, EMF generated by R minus d phi by dt. This is going to be the current induced. Yes, this one. It is simply Ohm's law, nothing else. Now, this is a special case. Let's talk about this one, a special case, which is mostly used in the questions. So please be very careful about this one. The condition is, this is a region of magnetic field, a constant magnetic field. Abhi, there is a let's connect the resistance over here, and this is a loop which is passing through this in this direction with the velocity v. Now there is no magnetic field passing through this loop, right? No magnetic field, so flux is going to be simply b into a, and v is 0 here, so 0, initial at 0. Now while moving in this direction until it reaches over here, the whole field, no field is passing through the area, right? So magnetic flux is simply non-existent over here. But the moment it crosses this section, yes, the moment it crosses its section, some part is inside the field and some part is outside the field. Now do you think while it is moving inside, the amount of flux is changing or not? Of course it is changing, because the area, जो भी एरिया जिसमें मैग्नेटिक फील्ड पास हो रहा है, दिस मच अमाउंट ऑफ एरिया, वो तो इंक्रीज हो रहा है ना विद टाइम. अगर ज्यादा कॉइल अंदर घुसते जाएगा मैग्नेटिक फील्ड में, तो यहाँ पर डेफिनेटली ईएमएफ जनरेट होगा. ओके, जनरेट होगा, नो प्रॉब्लम. नाउ this is at, let's say, time is equal to 0, and there is another condition that I'm drawing here. ये वही कॉइल है, बट इसने थोड़ा सा डिस्टेंस कवर कर लिया है इन डेल्टा टाइम t. दिस इज डिस्टेंस कवर्ड डेल्टा t. ऑलराइट, डेल्टा t टाइम में इसने इतना डिस्टेंस कवर किया है, और डेल्टा d in delta time t. Okay, no problem. Now, what is the change in flux over this delta time t? Can I say this is the amount of flux which has changed over the delta time t? Because ये वाला portion तो already था ही, अभी भी है, which is inside the field, which is in the part of the coil inside the field. This blue portion is the one that has been added up, right? Wait. I think I should erase this one. Yes. Initially this was the flux, and this was the flux, and now this portion has been added up. So I will calculate this much amount of area, right? The change in area, right? So the change in area is going to be the same length. ये जो length है वही तो ये लेंथ होगा, अदरवाइज सेम कैसे रह जाएगा? सर्किट का जो भी लेंथ है सेम ही तो है, चेंज तो नहीं हो जाएगा while entering into the flux region और magnetic field region. So हम क्या करेंगे यहाँ पर, डेल्टा टी, यस डेल्टा डी। तो यहाँ पर अगर इसको एल मान लो मैंने, एल, तो कितना मैग्नेटिक फ्लक्स चेंज हुआ है ओवर डेल्टा टाइम टी? डेल्टा फाई इज गोइंग टू बी this much amount of area, right? So delta d into L into the magnetic field. This is the flux. Now I have to do delta phi by delta t, right? So as to calculate the EMF generated. I'm not bothered about the sign over here because वो तो हम Lenz law से निकाल ही लेंगे. So delta d into L into B divided by delta t. Now what is this term? Delta d by delta t. This is nothing but rate of change of displacement, right? Or the, yes, rate of change of displacement. Isn't it the same as velocity? Yes. So BVL is going to be the EMF that gets generated in this system, where L is this distance. Please keep care. This is not L. No, this is the L. And B is the magnetic field, V is the velocity, which is perpendicular to the velocity, the component of velocity, which is perpendicular to the magnetic field. Now this is the magnetic flux, this EMF induced. If that is induced, then let's see whether we have got the same thing. Yes. And the current is going to be simply VBL by R, right? Why? Because this this circuit, where is that? Yes, this circuit, if it has a resistance of R and the EMF gets generated in the this thing is E, then it is going to be simply E is equal to I is equal to E by R, right? And E is simply BVL that we have already discussed over R. This is the current that will be generated due to this moving coil. Okay, this is the one. R is the resistance of the rod moving with velocity. Actually, you can take the rod to be having very low resistance, or the wire having low resistance, or even if you take the resistance, it is not going to create much change. It is just the total resistance I'm talking about. The EMF divided by the total resistance will give you the current. This is clear from the chapter of this thing, chapter of current electricity. Induced EMF, we have already talked about this one. Now let's come to this part, the power generated. First of all, the power consumed by the loop in this process is, what is that? V into I, no problem. So BVL into BVL upon R. This is the current, right? And this is the voltage. Isn't it the same as B square L square upon R? This is the power generated. But we have also to find out the force. What is going to be the force? For that, I will use something. Let's say what it basically talking about is, while moving inside the loop, as per Lenz law, this tries to oppose every type of change in the flux, right? As per Lenz law. So, as per Lenz law, we must experience some force in this direction, because this, as per Lenz law, it is trying to oppose the change in flux or change in increase in flux. That will happen only when it is repelled, right? And we have to find out the force. Now, let's see one thing. Due to this power consumption inside this circuit, some energy is being lost, right? Or consumed. Some energy is being consumed in the form of heat due to this resistor. Where is that energy coming from? Since the magnetic field is constant, it is not changing. The source of the magnetic field is not changing at all. Still, some energy is coming up, and it is getting lost in the power in the form of heat. Where is that coming from? the only energy which is available is the velocity or the kinetic energy. If the power, some of the energy is being consumed, it means the kinetic energy must be reduced. And how does the kinetic energy reduce? Only when the speed is also reduced. And when is speed reduced or velocity reduced? Only when there is an acceleration. And if there is an acceleration acting on the body, it means some force must be there. I hope you're able to link all these terms. So some force must be there which is reducing or retarding the flow, the movement of the coil. अभी coil move कर रहा है rightwards, उसमें increase कर रहा है flux, तो लेंज लॉ के हिसाब से उसको नहीं करना चाहिए ना, उसको उसको अपोज करेगा, तो अपोज करेगा तो उसको रुकना पड़ेगा लेफ्ट साइड में जाकर, और वो फोर्स लगाएगा, और वो हम फोर्स फाइंड करना चाह रहे हैं. नाउ is there some work done by this force? Of course, even if it is negative, there is some work done. Why? Because the force is being applied in this direction while it is moving in this direction. So of course there is a work done. Of course it is negative, but still there is work done. So work done by this force is nothing but FDS over some distance, small distance. And when you integrate, yes, this is the small work done. Now let's divide it with respect to time. What happens? dt. What is this? Rate of change of work. This is power is equal to F. Since force is constant, it remains the same. ds by dt. It is going to be the velocity. So simply, force is going to be power over velocity. And power we had already talked about, that the power consumed by the loop in the form of heat is this one. Then what is the power lost by the loop in form of kinetic energy? It should be the same as per the conservation of energy, law of conservation of energy. The power consumed by the loop should be equal to the power lost in the form of kinetic energy. So b square v square, okay, the whole thing, b square v square l square upon v. One of the v gets cancelled out, and hence you're left with b square v l square upon nothing. Wait, it was r, right? R. All right. So this is the power, or actually this is the force that is experienced by the loop. The same thing. And we have already talked about this one. I don't know why they are giving b again and again. Now this thing, until now what we have discussed is, if we have certain certain flux was representing in the form of, flux is equal to or the E in form of flux, right? But, or flux in form of B into area. But what about, we have a coil, let's say solenoid, and some current is passing through it. How do you do the calculation of flux in this one? You have to first find out the magnetic field getting generated by the I, and then multiplied by the area and all that. So you have to do directly multiple calculations to arrive at the flux. But we have identified that at the end it is directly proportional to the current itself, or the change in current. What we have defined over here is phi is equal to some constant multiplied by current. The more the current, the more the flux. This constant is called inductance. We are defining a new constant here. which is the result of proportionality between flux and the current, which is called inductance. And this inductance has a SI unit of Henry, H. This is the simple definition, connecting flux and the current. Now, if we do d phi by dt here, or differentiate both sides with respect to time, what are we going to get? dmi over dt. I already told you that this m is a inductance and it is a constant. It will come out of the differential. Yes. So d phi by dt is simply m di by dt. What is d phi by dt or minus d phi by dt? I have given both minus in both sides. What is d phi by dt? D phi by dt is simply EMF generated, right? Electromagnetic induction. Due to electromagnetic induction, the EMF generated is equal to minus m di by dt. So the rate of change of current, from that you can find out the induced EMF, induced, and that depends on the inductance of the. Inductance is simply a property of the coil. How much amount of magnetic field is getting generated, due to which the amount of EMF will be induced. And there is another thing called this is self inductance, right? This M is, or we also represent it with the form of L. Phi is equal to Li, inductance or self inductance due to itself. Now there could be another case in which this is one and this is another inductor in another circuit, maybe in another circuit. The current changing in this one would result into the change in flux in this one, right? Because this is a solenoid, it creates magnetic field around it in all directions. So it will also create magnetic field which is passing through the second solenoid, which is unconnected but in close proximity. अभी उसके वजह से मैं इसमें करंट बढ़ा दूंगा तो इसमें मैग्नेटिक फ्लक्स भी जो भी जाता रहेगा वो भी चेंज हो जाएगा, और इसमें अगर इसमें फोकस करो इस डब्बे में, तो मैग्नेटिक फ्लक्स इस सोलेनॉइड से जो पास हो रहा है वो चेंज हो रहा है, और उसके वजह से एक और ईएमएफ जनरेट होगा इनसाइड इट. दिस इज द सॉर्ट ऑफ, दिस इज अगेन इंडक्टर्स बट इट इज mutual, because one of them is inducing the second one, so it is called mutual inductance, given by the term m, and the same will be for this case. अगर इसमें भी सेम फिनोमेना हुआ तो ये भी इंडक्टेंस इसमें करेगा. सो द म्यूचुअल इंडक्टेंस m, एंड इसके वजह से जो भी होगा क्रिएट ईएमएफ, इट इज गोइंग टू बी द सेम. E is equal to minus m di by dt. जस्ट इंडक्टेंस की जगह म्यूचुअल इंडक्टेंस लगा देना है, बिकॉज द रिजल्ट इज गोइंग टू बी द सेम, राइट? इट्स जस्ट दैट रीजन, फर्स्ट ऑफ ऑल फर्स्ट केस में था कि खुद की वजह से इंडक्शन हो रहा है, और सेकंड केस में हो रहा है कि दूसरे की वजह से इंडक्शन हो रहा है, पर इंडक्शन तो हो रहा है दोनों केस में. सो दिस इज द म्यूचुअल इंडक्टेंस. And we have an expression that I don't think you need to remember, because in all of the questions that I have encountered, they're giving the inductance or the mutual inductance, the value itself. So you do not need to worry about, even in that case we'll look into it. Mu into n1 n2, where n is the number of turns in each of them, and pi r1 square into L. L is the length of this one. This is the inductance of one in the other, and inductance in the second due to one. Now this has been covered. E can be calculated in the same manner. NBA omega sin t. AC generator, AC, in AC current or in AC voltage, it is simply V is equal to V naught sin omega t. अभी यहाँ से अगर हम लाना चाहें तो आ जाएगा, no problem in that, because this changing voltage will give you changing current, and changing current will give you the changing magnetic flux और magnetic field, we will change the magnetic flux और वहां से link हो जाएगा. So I think this portion is clear. Self inductance I already told you. The first part I told you was about a single one. इसी में खुद में हो रहा है जो भी हो रहा है, कि इसमें करंट चेंज हो रहा है, इसी में मैग्नेटिक फ्लक्स चेंज हो रहा है, और इसी की वजह से एक और मैग्नेटिक ईएमएफ जनरेट हो रहा है, ईएमएफ इंड्यूस्ड. वो है इन सेल्फ इंड्यूस्ड, बट देयर कुड बी म्यूचुअल इंडक्शन एज वेल. Self induction and mutual induction is this one. Now we have something, this one. This talks about something. I'll just give you a brief idea about this one. Let's say, actually we'll talk about it in the next part, which is the AC current. Yes, AC. So I think this half portion of this thing is clear, right? Yeah, that is all you need to remember in this particular chapter. And coming to the next one, alternating current. Now, alternating current. First of all, before alternating current, I will give you certain circuits. What are the components that will be in there? अभी तक हमने जितना भी पढ़ा है, तो फर्स्ट चैप्टर में हमने कैपेसिटर्स के बारे में देखा, सेकंड चैप्टर में हमने रेजिस्टर्स के बारे में देखा, और थर्ड चैप्टर में हमने इंडक्टर्स के बारे में देखा. दिस इज द सिंबल फॉर इंडक्टर, CRL. What are the different combinations of circuits that you could generate? One combination could be RC circuit, second combination could be LR circuit, third combination could be LC circuit, the fourth combination could add all of them, LCR circuit. So we will look all of them. First of all, I think I had left one portion in the electrostatics that I had told that it will be discussed in this particular chapter, alternating current. This was RC circuit. This is one circuit in which it is connected to a battery where there is a resistance and there is a capacitor. Now, what happens is, initially the capacitor acts like no resistance. It helps in the conduction of electricity and current passes through it. But you know that what is the function of a capacitor? It stores charge, and after certain time, this portion, this wall of the capacitor will store some charge, positive, and this one a negative. What is the conduction of current? What is the particles responsible for conduction of current? These are electrons flowing in this direction that are resulting into the current. These are electrons flowing. It is opposite to the direction of current. So electrons are flowing now. If you give a very large charge on the right side wire or right side wall, then the incoming electrons will be repelled, right? They will be repelled, and after certain point, actually the whole capacitor is charged now, and it can no longer sustain the flow of current, because all the electrons which are coming to cross the capacitor are not able to cross it because they will get repelled. इलेक्ट्रॉन्स राइट, नेगेटिव चार्ज है, इसमें भी नेगेटिव चार्ज पूरा भरा पड़ा है, तो अगर यहाँ पर आएगा तो रिपेल तो हो ही जाएगा, लाइक चार्जेस रिपेल ईच अदर. तो इसकी वजह से ये फुल्ली चार्ज जो हो गया है उसमें अभी कोई करंट नहीं है ना. तो दिस इज अ ग्राफ दैट आई एम ड्रॉइंग हियर. इनिशियली करंट था, बट यहां पर करंट धीरे धीरे टाइम के साथ लूज हो रहा है. आई एंड दिस टाइम, it is going to be like this, exponential होता है डीके, एक्सपोनेंशियल डिक्रीज होता है, एक्सपोनेंशियल। अगर एक्सपोनेंशियल है तो ई टू द पावर और सम कांस्टेंट टू द पावर होना चाहिए, टाइम का वेरिएबल, राइट? ई टू द पावर टी और some constant c to the power t. That is why the current at any time I at t is given uh, in this situation as I naught 1 minus e to the power minus uh, t by rc. All right. This is the formula for current inside the RC circuit for RC. As you can see that as time passes, it will go to 0. Wait. I think there was a slight mistake in this one. Yes. I naught. This is the formula for RC circuit. It will grow with time. Why? Because when you plug t is equal to 0, e to the power 0 is 1. So I naught. I is equal to I naught. And what is I naught? I naught is simply this value, the maximum current. And what is the maximum current? How can you find the maximum current? अभी सर्किट में अगर इनिशियली कोई रेजिस्टेंस नहीं था ड्यू टू द कैपेसिटर, देन वी कैन अज्यूम इट टू बी अ सिंपल कंडीशन, राइट? एक बैटरी है और एक रेजिस्टर है, तो यहाँ पर करंट कितना होगा? सिंपली V by R. So I naught could be written as V by R. This is the RC circuit. In a similar pattern, there is an LR circuit. R inductor. Battery. Now, अभी इसमें क्या होता है? Actually इसमें opposite होता है. That initially the current is trying to flow, but it is getting repelled. Why? Because the moment you plug the battery or switch on the battery, some current is getting generated, which generates magnetic flux inside this coil, and due to this sudden change in magnetic flux, there will be huge potential generated in the opposite direction, due to which it looks something like this, or something like this. Due to the huge, this is EMF generated, induced, and this is EMF initially. So due to this, it actually doesn't allow any uh, this is trying to start the flow of current, right? And this is stopping the flow of current. This is why initially uh, there is no electricity flowing inside the loop, due to this inductor, due to the induced EMF in the opposite direction. And as time passes, some current starts to flow. Why? Because the flux is now getting stabilized now, and while it is getting stabilized, the change in flux is now reduced. If the change in flux is reduced, the EMF getting generated induced is reduced. So that is why it will overpower, this battery will overpower the induced EMF that is reducing with time, and some current will start to flow. This graph for this one looks something like this. It is also exponential, but it is exponential increase. This is I and this is time. The growth looks like something like this. After certain time, it will almost reach a plateau with a fixed current. So for this one, see, where was I? Yes, we were discussing this portion, the growth of current. So in this case, I at as a variable time looks like yes, e to the uh, I naught 1 minus e to the power minus t r by L. Now, at a very long time, this inductor will not actually change, no flux will change into it. So it will act as a straight wire, and this at the very long time, this will look something like this, because the inductor offers no resistance now. This is R. So the maximum current which is flowing now, it is the same as V by R. So I at time t is equal to V by R e to the power R upon L. Alright. So this is the growth of current. This is the one we are talking about. And decay of current, actually, I'll talk about it. What is the decay of current? Let's say there is a condition that now the maximum current is flowing through it. And suddenly what I do is I join it, connecting this one out. Let the this thing come out, the battery is out, and suddenly a wire has been replaced. Now suddenly there is no I has been reduced to very low, right? Why? Because there is no battery source, due to which the magnetic flux already here is now getting reduced at a fast pace, due to which again current will start to flow, right? And that will be decay of current, and the graph will look something like this. Initially there will be huge induced EMF because of sudden loss of flux, and it will go to zero with some time. Exponential decay, and yes, it will have almost the same property. I is equal to I naught, but not 1 minus, it is simply e to the power minus tr upon L. So this was for the constant source of potential. But in this case, in this chapter, we are talking about alternating current, which means varying power. It means, or sorry, varying source of voltage. The in normal cases, the voltage looks something like this, right? Voltage with time, it is a constant. But in alternating source, it looks something like this: a sine wave or a cos wave. So sine, and the voltage could be written as, if this is the maximum V maximum, so V could be written, V as a function of time could be written as V naught, which, or V maximum, into sine omega t. Omega is the angular frequency. All right. So this is the source that I'm talking about. And let's talk about something called root mean square. Why? Because if you want to find out the average over this whole portion, from this to this, what is going to be the average voltage? Zero, because it is a positive part and it is a negative part. You will add them up and it will become zero. But over the time, do you think it has no effect? It does have effect, right? That is why we take not average, we do not take, we rather take root mean square, VRMS. Root mean square is simply, you're adding the individual terms, right? But in this, what we add is actually the square term. When you take square, the whole thing becomes something like this. Why? Because even this portion, negative portion, when you square it, it becomes positive, and the graph looks something like this. Now you can take an average and you take an under root. So basically it looks like V is equal to, or VRMS is equal to under root V1 square plus V2 square plus V3 square, like that. So VRMS in this case is actually, when you calculate that, it is actually V maximum upon root 2. All right. Now, if there is a resistance conducted, or resistor connected to the alternating source, it is representation of this alternating source of voltage. then the current will also depend in the same fashion, right? So the current will also look something like this, I versus T. So for the current as well, the RMS will be I by root 2. This is RMS value, and this I don't think is very useful in this case. It's just that RMS value, it is fine. It's just that reverse is written over here. If I RMS is equal to I naught over root 2, then I naught is equal to root 2 RMS, I RMS. Now, if this is clear, let's talk about something called impedance and reactance and all. So let's take this one. This is resistance, right? But is this resistance or is this resistance? No, they are capacitance and inductance. But how to find the effect of these in the current? That will represent by a term called reactance X, and this is C. We calculate that is equal to 1 by omega C. Omega is the angular frequency of the alternating source, and this is XL is equal to omega L. This you have to remember. And the opposite, the effect of each of them is opposite. Why? I already told you that the graph looks exactly opposite to each other. That is why the effect of a capacitor and inductors are always opposite. That is why these are reactances, and the total reactance X is equal to XL minus XC. That is 1 by, sorry, omega L minus 1 by omega C. This is called reactance, total reactance. This is capacitive reactance, and this is inductive reactance. There is another thing called impedance. Let's say you have all the things combined. Then the whole thing combined gives you an obstruction, right, to the flow of current. Now we cannot term it resistance. Why? Because we already have taken it for the only this part resistor. That is why we give the name impedance. How much it is impeding the flow of current. So impedance is simply Z is equal to, just a second, R square plus XL minus XC the whole square. So basically omega L minus 1 by omega C the whole thing squared. Why I'm writing this as it is, I'll tell you now. Because in the case of an in the case of which one, L, let's say in case of L or inductor, this is an inductor and this is a alternating source. With the moment it is 0, it is going to be maximum, right? And the moment it is maximum, it is going to be 0, as we have understood in this case. That is why the current leads, I leads in the inductance, and I lags in the capacitance by the same amount, pi by 2. Pi by 2 is in the form of this one. The maximum takes place at pi by 2, right? So that is the same amount of phase angle through which it leads and it lags the capacitance. I leads V, and this I leads V in the case of capacitance by pi by 2. If this is clear, then I can draw something called a phasor diagram, because the current in resistance, let's take in this direction, then the current in either the inductor or the capacitor is going to be perpendicular to the resistor, right? If this represents the resistor, it will be perpendicular. Why? Because it always lags or leads by pi by 2. Then this is reactance in the of the inductor, and this one is reactance of the capacitor. Both of them make a 90-degree because pi by 2 with respect to voltage and pi by 2 with respect to voltage. One is plus pi by 2, one is minus pi by 2. So this is 1 by omega c and this is omega L. Alright. Now the effect of this and this are opposite to each other, and I can represent this one in the format of this R, and this is simply omega L minus 1 by omega c, or in other words X. So if I take both of them, the total impedance is always, they are perpendicular to each other. When you want to add them up, it is going to be this vector which is called impedance, which is r square and this x square. So z is equal to under root r square plus x square, and what is x? This much amount, r square plus 1 omega L minus 1 by omega c, the whole thing is squared, and this is the general equation for impedance. Alright, so impedance, and impedance is simply E by I. How do you find impedance? Simply the voltage at that point divided by the current at that point. We have already talked about impedance and reactance. Now, yes, they have given different these things, but we'll talk them about them in a very general sense. You do not have to remember all this. I'll give you a separate list or a very general list that that will combine all of them. You do not have to worry about individual circuits and remembering all of them. No, I'll give you a general circuit, LCR circuit, R, C, and inductor L, and this has been connected to a battery, this. Then what are the things that we need? We'll need phase angle, power, nothing else. All these boxes have given the same thing. I will give you in a very short format that you can apply in all of the combinations. First of all, the phasor diagram. What was the phasor diagram? Yes, this was the phasor diagram that you have to look into it. This is called phasor angle, or phi, sometimes represented as phi. This is called phasor angle, and the power consumed simply, first of all, how do you find the phasor angle? Either in form of tan theta, or you can even use cos theta. Cos theta is easier because cos theta is used somewhere else as well. So cos theta or cos phi, in this case, what is that? Cos phi, it is base divided by the hypotenuse, so simply r by z, right? So cos theta, cos phi is r by z, or r over under root r square plus omega L minus 1 by omega c, the whole thing is squared. Now you have this equation that you need to remember. I'll just give you these simple a few formula that will help you in all of the different combinations: RC circuit, LC circuit, LCR circuit, all of that. The power consumed, there is a simple formula: VRMS IRMS cos phi, where cos phi you can find it from here. This is another formula. This formula and this formula will sort all of the circuits. Why? Let's take RC circuit. In this, L is going to be 0. So you just plug the value of L to be 0 over here, and the rest you will get simply the rest of the terms. And in finding cos phi, yes, when you, let's say you have LC circuit. LC circuit. In LC circuit, you just plug the value of R to be 0 because there is no R, and you'll be left with cos phi is equal to 0 and rest of that. So these two formula, if you remember, all of the circuits could be possibly found out. There is a special case that I'll discuss here, sorry, in which there is only a capacitor and as an inductor, or there could be, yes. This circuit is said to be in resonance. When is that resonance? It is when the total x is 0. Total x. When is the total x 0? Omega L minus omega C is equal to 0. So omega L is equal to 1 by omega C. In that case, omega square is equal to 1 by LC. In the case when omega is equal to 1 by root LC, that is the condition for resonance. It means they resonate with each other in this case. So this is one special case. Otherwise, most of the problems could be done in these two formula itself. Nothing else that you need to remember. And there is a simple thing that current leads voltage by phi, where phi you already know by this formula. The rest of it you do not have to remember all these individual boxes. You just have to remember these two formula and you will be done. That is it from the this we have already discussed. That is it from the this chapter, and we'll meet in the next one.